talking on. So that with that, I give the floor to Amit Behera, who is talking about almost public quantum coins.
Thank you, Marco. Hi, I'm Amit Behera from Ben-Gurion University. And today I'm going to talk about almost public quantum coins, which is a joint work with my advisor, or Sattath. I would like to thank QIP for giving me this opportunity to present my work, and also Auth for his continued guidance throughout this project. So let's get started. So my presentation will be in 5 parts. First, I'll give a short introduction to quantum money, followed by a little discussion of our previous works and our contributions, and then our construction, followed by the security definitions and our main results. And at the end, I'll show 2 technical results. Okay, so let's get started. So, can money schemes be unforgeable? Well, classically, that's not possible. Why? Because in the classical world, all the classical strings can be easily cloned. But in a quantum world, you can. So what do I mean by quantum money? So it's a triplet of algorithm: keygen, mint, and verify. So the bank does the keygen and generates a secret key. And using the secret key and the mint algorithm generates money states that are then given to the users. And any alleged money state can be verified using the verify algorithm. Now, based on the method of verification, quantum money can be categorized into 2 ways. Firstly, private quantum money. Here, key generation, the bank does the key generation and it generates a secret key. And whenever someone comes up with an alleged money state and you want to verify it, you have to go to the bank who will verify it for you. Now, in this case, only the bank can verify it because the verification requires a secret key. Whereas in the public quantum money setting, the key generation that the bank does also generates a public key, which is then broadcasted to the world. And therefore, whenever someone gives you an alleged money state, you can verify it by yourself using the public key. This is what we call the public verification. All right. Another classification of quantum money can be between coins and bills. Now, this classification even holds in our traditional money schemes. So coins are indistinguishable copies, whereas bills have unique serial numbers that set them apart. But why should we care about that? So we should care about that because these unique serial numbers can be used to track down transaction via bills. So in terms of privacy, coins are better than bills. Now let's look at some of the previous works. So for quantum money, there are quite a few private quantum money constructions, starting from the seminal work of Wisner's quantum money. There is Gavinski's classically verified quantum money, and a lot many other constructions. There are few construction in the public quantum money setting as well. But the important thing is that there has been no public quantum money construction which is provably secure based on weak and generic assumptions. Now, if we zoom into quantum coins specifically, there are quite a few construction for private quantum coin scheme. So the first construction was given by Mosca and Stebila in 2010. The construction was unforgeable, but it was inefficient. We didn't know how to do the mint and verify efficiently. Then came the G, Liu, and Song construction in 2018. So their construction was efficient, but it relied on a very weak computational assumption, namely the existence of quantum secure one-way functions. And very recently, Allergic Minds and Results came up with a construction which is efficient. It doesn't even require any computational assumption. However, it is memory dependent. So what do I mean by memory dependent? So the bank in this money scheme maintains an internal quantum state which gets updated with every mint and verify query. So obviously such a money scheme has this drawback that you cannot have multiple branches because you have to maintain an internal state. Okay. Again, in the public quantum coin construction, there has been no construction. So there has been no candidate construction before our work. So what do we achieve in our work? So we first give a construction of an almost public quantum money from standard assumption, namely up to the existence of quantum secure one-way function. And our construction is a quantum coin scheme, and hence this gives the first construction of public quantum coins. We also talk about other meaningful notions of security, that is other than unforgivability, which are important but has not received much attention so far. And finally, we put forward this notion of comparison-based verification, which is our main technique for the construction. And we think it might be useful in other areas as well. All right, so let's get into a construction. So first, I would like to illustrate our main technique, which is comparison-based verification. So for that, assume you are in a foreign land and you don't know anything about the currency of that land. And now you took some money from the ATM, and then later someone gave you money, maybe you did some transaction and someone gave you money. So since you don't know the currency, you don't know how to verify. So what can you do? So what you can do is that take this money and take the money from the wallet and check if they look the same or not. If they look the same, then you accept, otherwise reject. And what's important for this method to work, that money states should be identical. Hence it works for coins but not for bills. And other than that, you don't require any other specific security feature from the money scheme. All right. So what's the main challenge in translating this story into the quantum world? So the main problem is, how do you compare two quantum states? Classical strings, you know, you can easily look at them and know what they are. But that's not possible quantumly. So one option can be to use swap test. So just to remind you what swap test does, if you have two states psi and phi and you wanted to compare them using the swap test, then basically you run this circuit, and then according to the measurement outcome here, you either accept or reject. But the problem with swap test is that if you have two product states, two unentangled product states, then it will always accept with probability at least half. And that is bad if you want to use swap test for verification in quantum money. Why? Because 0 to 1 forging becomes possible. So the adversary can, who doesn't have any money state, he can send you any garbage state, and you will use one valid money state from your wallet to compare, and then run the swap test, and it will accept with probability at least half. So that's bad, because then 0 to 1 forging becomes possible with probability at least half. Okay, so what's the solution? So what we do is called the symmetric subspace projective measurement. You can think of it as an extension of the swap test. So basically in this case, we think that each coin, rather than being a register, is actually made up of k registers or k mini coins. So verification works as follows. Whenever someone gives you an alleged money state, it is also k registers, and you bring out one money state which is also k registers from your wallet. So you have two k registers, and you do a projective measurement into the symmetric subspace of these two k registers. So formally, what do I mean? Suppose you have a private quantum coin construction with keygen, mint, and verify, and say here mil represents one private quantum coin. Then the public quantum coin construction goes as follows. The keygen is same as the private keygen, and mint is basically repeating the private mint k times. So a public coin represented here as a cent is basically k copies of mil. So this is to give the analogy between cents and mils. So as you might be aware of, in various countries, a mil is like 1/10 of a cent. And even though they are not used in transaction directly by the users, they do exist behind the scenes. Okay, now let's see what is the verification. So verify is simple, as you might have guessed, it's comparison-based verification. So you take out one, if you have an alleged money state, you take out one money state from your wallet, and you do the symmetric subspace measurement on this entire state. So formally, what is symmetric subspace? So symmetric subspace over M registers is basically the set of all M register pure states that are invariant under any permutation of these M registers. And you can show that this forms a subspace of the Hilbert space. All right. Now that we have seen our construction, let's see the security definitions followed by our main results. So let's start with unforgivability. So in an unforgivability game, what happens is that there's a challenger and an adversary. The challenger runs the keygen and the mint and sends n money states to the adversary. The adversary does something fishy and sends m money states. You can think m greater than n. And the challenger runs verify on each of these m states. And traditionally, unforgivability means that with overwhelming probability, the number of successful verifications that the adversary manages to pass should be at most n. However, this notion of unforgivability is too strong to achieve for our construction. Hence, we give a weak but meaningful notion of security, which we call rational unforgivability. So in rational unforgivability, all we want is that expected number of successful verifications that the adversary manages to pass should be at most n. Now, this is a meaningful notion of security in real world because most of the adversaries in the real world are rational entities. So if the adversary is a rational entity, then he will not try to cheat because he will see that the expected number of successful verifications he could get is at most n. So he's not gaining anything on average by deviating from the honest protocol, so will not try to cheat. All right, but usually in quantum money we only talk about unforgivability. But is unforgivability enough? Consider the following. Suppose some potentially adversarial merchant gave you a money state, you ran the honest verify and you got and you accepted the coin. And then when you try to pay it forward, it didn't get accepted. So you sent it to someone else. He ran the honest verify, but then it didn't pass the verification. So in this case, we have been sabotaged. And note that these kind of attacks are not disallowed by unforgivability or completeness. So at least in the general setting, no. Okay. So we formalize the sabotage game. So in the sabotage game, as you can imagine, there are two merchants, merchant 1 and merchant 2. Merchant 1 is the one targeted by the adversary. So the adversary sends M money states, M alleged money states, and the merchant 1 runs verify on each of them, and then pays it forward to merchant 2, who also runs verify on each of them. Now let accept 1 be the number of coins of the adversary that merchant 1 accepts, and accept 2 be the number of coins of merchant 1 that merchant 2 accepted. Then standard security against sabotage will basically mean that with overwhelming probability, accept 1 should be at most accept 2. Whereas rational security against sabotage will basically mean that on expectation, accept 1 should be at most accept 2. So now that we have defined our security definitions, let's get to our main results. So we show a lifting result. So what do I mean by that? Suppose you have an unforgeable private quantum coin scheme, such as one of those three schemes that we mentioned earlier, MS10, JLS18, or MR20, and you feed it to our construction. That is, you instantiate our construction with this private quantum coin scheme. Then what you get is a rationally secure public quantum coin scheme. So in particular, if you use the JLS18 scheme as the private scheme, as the private money scheme in our construction to instantiate our construction, then also you get a rationally secure public quantum coin scheme. And since JLS18 is based on one-way functions, what this gives us is our main result that says that existence of one-way functions imply the existence of rationally secure public quantum coins. So we can also try to instantiate our construction with the other two private quantum coin scheme, in which case the resulting public quantum coin will suffer and enjoy from the same properties as of the underlying private quantum coin scheme. All right. So our construction as a public quantum coin scheme has the following negatives. Firstly, it's only satisfy rational security and not the standard security, so rational security is a weaker form of security, but a meaningful form that we have mentioned earlier. And secondly, note that for every transaction you receive, you need a fresh coin in our construction to verify it. So you might think that if you run out of fresh coins, you have to go back to the bank to get fresh coins. Now, this is bad from a public quantum coins point of view. But on the upside, firstly, rational security isn't that bad. Why? Because real-world adversaries are actually rational entities. And secondly, this requirement of a fresh coin for every received transaction isn't much of a hassle from a public point of view. Why? Because suppose you withdraw $100, so you have 10,000 cents. So you would be good to receive 10,000 transaction. You can verify 10,000 transaction with those 10,000 cents. Now, so if you can verify that many coins, then you might not have to go to the bank that frequently. So in a nutshell, what I want to say that if you start off with a lot of cents, in our case even 100 cents, which will mean $100, which will mean 10,000 cents, then you won't have to go to the bank very frequently. You might have to go to the bank only once in a while. So from a practical point of view, our construction is as good as a public quantum coin scheme. And we believe this solves an important open problem. Next, we'll show two technical results regarding our construction. So first, we'll show that our construction is 0 to 1 unforgeable. And next, after that, I'll show the optimal end-to-end plus one forgery for our construction. So what is 0 to 1 unforgeability? So here the adversary starts with no cents, 0 cents, and is trying to pass one verification. So he sends one alleged cent, which is like K register state phi. So from now on, we do the simplification that mil is like ket1 and a cent is therefore ket1 tensored K. So now since the adversary didn't start off with any mils as well, if you do standard measurement on each of the K registers of phi, then the Hamming weight of the measurement outcome should be 0. Otherwise, this would have been a forging against the private scheme, the underlying private scheme, and which is not possible because we assume that the underlying private scheme is unforgeable. Hence, this state phi should be very close to the state 0 tensor K. So now let's see what happens when you try to verify it. So you take out a cent from your wallet, which is like 1/10 K, and you have this state phi, which is like 0/10 K, and you do this projective measurement into the symmetric subspace. So either it gets rejected, in which case this whole state collapses to a simple state, that is, it gets projected into the orthogonal subspace of the symmetric space, or it collapses to a symmetric state, in which case you can show that it must collapse to this particular symmetric state. Why? Because look here, the Hamming weight of the state is K, so a product state with Hamming weight K, and so it must collapse to this uniform superposition of product states with Hamming weight K. And hence the acceptance probability is basically the fidelity between the state here and the state here, which you can imagine should be 1/2K choose K. And for K large enough, this is negligible. Since our arguments hold for any arbitrary phi that the adversary submits, we conclude that our construction is 0 to 1 unforgivable. Next, I would like to show the optimal n to n plus 1 forgery. So in this case, the adversary receives n cents, which you can think of as nk registers, and is trying to pass n plus 1 verification. So he sends n plus 1 coins, n plus 1 alleged cents, which is like n plus 1 k register state phi. Now again, I would just like to remind you that a cent is like 1/10 K. And again, by the unforgivability of the private quantum coin scheme, if you do standard measurement on each of the n plus 1k registers of phi, then the Hamming weight of the measurement outcome would be at most nk. Okay, and again, what happens when you try to verify? So you take out a cent from your wallet and you do this verification. So you either reject, that is, it collapses to the orthogonal subspace of the symmetric subspace, or you accept, in which case the acceptance probability is basically this overlap, and hence the forgery probability of this forger is given by this expression. And this is what the adversary is trying to maximize over phi, and he has this following constraint. So now we will try to simplify the maximization for the adversary using a property of the symmetric subspace. So what is this property? So it basically says that if you have phi as a symmetric phi, an n plus 1k register state which is orthogonal to the symmetric subspace, then 1/10 k tensor phi is also orthogonal to the symmetric subspace. And this holds because of this very basic fact that if you have an n plus 1k register symmetric state, so if you have, so say you have a three register symmetric state, you don't even have to think that large, then any 2 register subsystem of it is also symmetric. And what does this property gives us? So we have this following maximization from the adversary's point of view. Now this property basically tells you that there exists a state in the symmetric subspace that maximizes it. So from now on, the adversary will only try to find a symmetric state that maximizes this forging probability subject to this constraint. Okay. Now, in order to find this optimal symmetric state, we will use the basis for the symmetric subspace. So suppose you have a symmetric subspace over m registers, then this particular set forms an orthonormal basis for the symmetric subspace, where sim j is given by the uniform superposition over product states with Hamming weight j. Now, so firstly, you can show that this does form an orthonormal basis for the symmetric subspace, and moreover, it satisfies the following properties. Firstly, if you do standard measurement on this sim j, like you do standard measurement on each of the m registers of this sim j, then the Hamming weight of the measurement outcome will be j. Why? Because it's simple to see that this is each of the summand in the sim appearing in the sim j has Hamming weight j. Okay. Moreover, so we said semis are orthogonal to each other. Hence, 1/10 k tensor semis are also orthogonal to each other. But the second bullet basically says that they remain orthogonal even after you apply this projector, pi-sim projector, the projector into the symmetric subspace. And thirdly, this expression given here scales as m choose j by m plus k choose j plus k, m plus k choose j plus k, which increases with increase in j. But why are we concerned about this expression? Well, if you think, then suppose you are an adversary and you are forced to, in that n to n plus 1 forgery, you are forced to submit a sim j as your phi, then this basically gives you your forging probability. So you would like to maximize it, and hence you will try to send a SIMJ with the largest possible J, because this forging probability increases with increasing J. Okay. Now let's get back to the end-to-end plus one forging. So this was the adversary's maximization that the adversary was trying to do. It had two constraints, and you wanted to maximize over 5. The first constraint, of course, corresponded to the unforgivability of the private quantum coin scheme. Now, by the first two properties of the basis here, you can convince yourself that there exists an phi in this subset of the basis that maximizes it. You don't have to look beyond it. I mean, to be more precise here, since the Hamming weight on measuring SIMJ is J, you would only have to look at the span of these things, J less than equal to NK because of this constraint. But then by the second bullet, you don't have to look at the span. It's enough to just look at this like this subset itself, because the cross terms get cancelled off. And finally, by the third bullet, or the third property of the basis that we showed, that we saw in the previous slide, phi optimal should be sim nk. Why? We should increase J, because then only the optimal forgery increases, so that J can go till nk. And hence the optimal forgery probability is given by this expression, which turns out to be 1 minus 1 by n to the power k. And now this is a large number, right? It goes to 1 as n goes to infinity, and hence clearly our construction is not standard unforgeable. However, this optimal forgery probability can be used to show that our construction is indeed rationally unforgeable, and that's what we do in our paper. So for more details, please look there. And this concludes our discussion about end-to-end plus one forgery. So now to summarize, we first saw that our construction is 0 to 1 unforgeable, and secondly we saw the optimal end-to-end plus one forgery for our construction. So that in one hand gives you that our construction is standard forgeable. However, it can be used to, this optimal forgery probability can be used to show that our construction is rationally unforgeable. So the second statement we didn't really show, but I would like to encourage the audience to see the paper for more details. And now I would like to conclude with two open questions. So firstly, we gave this notion of comparison-based verification, which we think is a very general technique and can be useful in areas adjoining quantum money, such as quantum copy protection, secure software leasing, unclonable encryptions, tokens for digital signatures, etc. So we encourage further research in this direction. And secondly, we gave a construction of a rationally unforgeable public quantum coin scheme from standard assumptions. But the question of standard unforgeable, or the traditionally what unforgeability means, the standard unforgeable public quantum coin scheme, or for that matter, even public quantum money scheme from standard assumption, that still remains open. And with that, I would like to conclude. Thank you.
Okay, thank you very much. So I'm still watching Slack if there are more questions. So one that came up is, what's actually the difference between your approach and just using n times a swap test?
Okay. So our approach is a stronger. So like so if I think correctly, so doing n swap test is weaker than doing this symmetric substrate verification. Why? Because so remember, one of the properties that I mentioned was that if a 3-register state is symmetric, then any 2-register subsystem of it is also symmetric. So if it passes n parallel swap test, if it passes our symmetric substrate verification, then it will also pass the n parallel swap test. So the probability of passing n parallel swap test is greater than the probability of passing our our symmetric substrate verification. So in some sense, our method is a stronger form of verification than that, and I think it is crucial as well. Yeah, I think we actually thought of that initially, but then we came up with an attack in that case, even in the rational setting.
Okay, thanks. And I have one more question which concerns the setup. So maybe I misunderstood this a bit. So in order to verify coin, you need to have a copy of that coin, right?
Right. Like a coin from the bank, like the fresh coin from the bank. Yeah.
Yes. So if you get these fresh coins, wouldn't it be, and you need to get more of them from the bank to do your verifications, wouldn't it then be rational to try to cheat and just ask for new coins for verification purposes after?
No, so it's not like the bank is giving you coins for free, right? I mean, okay. I think I got the question. So in some sense, so we also have some specialized, like a different algorithm, which we call the refund algorithm. So you can take your money and give it to the bank. The bank has a secret key and it does a refund for you and gives you fresh coins. So this is how like used money is translated back to fresh money to your wallet. So then you can use this fresh money to do transactions. So it's not like that. It's not like that you are given that money for free. So it's basically you will take, so you did some transaction, you have some money with you. They might not be fresh, but they might not be fresh coins from the bank, but so it's kind of used money. So you can take this money to the bank and do the refund and get fresh money back, and then use it again for receiving transactions. Is that clear? Maybe I can elaborate it more in the round table.
Yeah, maybe. So there's no difference, right, between the money you use for verification and the one you use for actual payments.
No, so okay. So when you get money from the bank, it's like fresh coins from the bank. So it's like cents, right? But as you use them in a transaction, they might change. The quantum state might change, and hence you cannot use them to receive another transaction. But you can use them to pay. Like you can always pay it forward, but you cannot use it as your standard to verify received money. So that's why after some transactions, you can go to the bank to get a refund.
Okay. Okay, so I don't see any other questions on Slack at the moment. So maybe we just thank you again and take a short break. Thanks.